Okay, welcome everybody to the second ITS seminar of the fall quarter. Today it's my pleasure to introduce Vikash Gayah as our speaker. He's an associate professor in the Department of Civil and Environmental Engineering at Pennsylvania State University. He received his bachelor and master's degrees from the University of Central Florida and his PhD from the University of California, Berkeley. He worked on research contracts valued at more than $5 million, sponsored by several state DOTs and the US DOT and other federal agencies. His research focused on urban mobility, traffic operations, traffic flow theory, traffic safety, and public transportation. And he has authored more than 50 peer-reviewed journal articles, over 50 referee conference proceedings, and numerous research reports to sponsors. Today's presentation is on the perimeter measuring control for two region urban networks, a deep reinforcement learning approach. And he has graciously agreed to answer the clarification questions during the presentation, so you can write them in the chat and I will monitor them and let him know that there are questions. And since it's a small group, at the end, maybe we can ask other questions by unmuting yourself and have a more informal conversation. And without further ado, Vikash, the floor is all yours.
Sure thing. And since it is a small group, and I think you guys are all sort of PhD students in the program, we could also just chat about other things after the presentation is done as well, not just the presentation if there's anything of interest. So thank you so much for arranging, Irene, and Wenlong, really appreciate the invite. I sort of invited myself, and part of the reason is I was just really interested in sharing this work. And so, as was mentioned, the title of the talk is Perimeter Metering Control for Two Region Urban Networks Using Deep Reinforcement Learning. Before I move on to the specific talk itself, I just wanted to acknowledge, make some acknowledgements. First, the work absolutely could not be completed without my PhD student, Dongchin Zhou. He's my PhD student, second year PhD student who's just sort of taken to this topic and has done a fantastic job. And so this is sort of the initial exploration into his PhD, which we're going to be doing, moving on with over the next few years. And then the work has been funded by a few agencies, National Science Foundation and the Penn State Institute for Computational and Data Sciences. So why am I so excited about this work? Well, this is sort of a continuation of my PhD work into the area of macroscopic fundamental diagrams. And so to kind of start off on a quick description of that, essentially macroscopic fundamental diagrams are useful tools to model transportation networks, complicated urban transportation networks. So pictured here is downtown San Francisco, just a small portion of downtown San Francisco. And so if you wanted to model the behavior of traffic in this fairly simplistic network, and I say simplistic because it's not very complex, but it turns out even just a very simple grid network like this is made up of hundreds to thousands of elements with thousands to millions of vehicles moving on it. And so they're so complex. If I wanted to model this, I would have to describe this network as each of these individual components. And these components consist of individual links, so the specific roadways, or nodes where the roadways meet and individual intersections. And I would need to model each one of these in a great deal of detail. So if you're not familiar with a macroscopic fundamental diagram, that's a new approach that basically says, listen, if we don't care about where vehicles are on any of these individual links in downtown San Francisco, what if I just wanted to model San Francisco as a whole? So I draw a big circle or a big ring around this downtown network. If I didn't care about the details of where individual vehicles are within this network, and I just wanted to know something about how well the network was operating, is it congested? Is it not congested? How congested is it? How productive is it? How quickly vehicles can find their way off of the network and exit, get to their destination? Then we can leverage these macroscopic fundamental diagrams. They work really well when a network is homogeneous, which means that made up of sort of similar street types, and traffic is relatively homogeneously distributed. So meaning like this area of the network has about the same density of vehicles as this area of the network. It doesn't have to be exact, but fairly similar. Okay. If that's not the case, well, we can just break that big region up into subregions, several subregions, and we can model the behavior of each of those several subnetworks or subregions. And this works because it relies on the existence of well-defined relationships between how productive a network is, that can be measured in average flow, total vehicle miles traveled per unit time, the rate that trips can be completed, versus the level of use, so the accumulation of vehicles on the network or the density. Okay, we've probably, as PhD students in transportation, we've probably seen relationships between density and flow for individual links. And it turns out that in some cases, if I average the behavior on many, many links that make up a downtown San Francisco or something like that, I get a very similar reproducible relationship where I know the average flow for a given level of average density. If that's true, then again, I just need to know how many vehicles are in each one of these regions, and I can take this network and I can model it as, instead of these thousands of links and intersections and things like that, I can model it as just a handful of regions and focus on how vehicles move from, say, one region to another. So I can take this very, very complex network with many, many pieces and simplify that into fewer pieces, which makes the modeling much more simplistic. So why is this useful? I mean, it's useful. Yes, it's more simple, but it turns out that it allows us to understand things, or to sort of develop traffic control strategies in a little bit more insightful way. So there have been various types of traffic control strategies that have been developed using these microscopic fundamental diagram approach. For example, one is congestion pricing. We can use this MFD-based approach, or this modeling approach, to kind of figure out, well, how much do vehicles need to pay if they go from a less congested region to a more congested region? If they're making that trip, how much do they have to pay? And that can be a function of how productive the region, the network is, how congested it is, and we can develop different types of congestion pricing frameworks. This has been done quite a lot in the research literature. We can use this as a tool for space allocation. We can divide up the network and learn a little bit about how much space or road space should I allocate to cars versus buses versus mixed traffic, how, in terms of dedicated bus lanes. So we can use that to understand how do we divide up the road space among competing modes. I've personally used this as a tool to study street network design, particularly related to one-way streets versus two-way streets, restricting left turns. We can use it as a sort of a macroscopic tool to understand how well the network would operate under different conditions, and then we can sort of learn different types of design or street network design, answer these types of questions. We can also use it just for macroscopic routing, not like a Google Maps routing, like which links do you take, but just generally, if I wanted to go from one area to another area, which macroscopic path do I want to travel? Do I want to travel sort of on the northern section, on the southern section, kind of in the middle? And so we call that sort of like a macroscopic level vehicle routing. And there's been a lot of work on that. But the most notable example is what we call perimeter metering control. So perimeter metering control, what it is I have this region of a network. So this is my downtown San Francisco, for example. And I have some key locations where vehicles are able to enter downtown San Francisco. San Francisco is really nice because there's several bridges that lead directly into the downtown. And then, of course, some surface streets as well. But the bridges are like key bottlenecks. And so perimeter metering control is, how can I limit the rate that vehicles are allowed to enter this downtown San Francisco, or this critical area of the network? How can I limit it to maximize the efficiency of the network and make sure the travel time for all vehicles is minimized? So we can by limiting the rate that vehicles enter this region, we can actually reduce the travel time for all vehicles. Maybe not every single vehicle individually, but sort of the total travel time for all vehicles. And this can be implemented in a variety of ways. We can use traffic signals to do that, so we can say, okay, well, these entering links, we're going to reduce the travel time to reduce the rate that vehicles enter. We can increase the travel time when the network is less congested. We can reduce the travel time when the green time when the network is more congested, to again limit how many vehicles are able to enter the network. And the idea is to keep the network from getting congested so it operates at its maximum productivity. So the reason behind perimeter metering control is, if we let people enter a network sort of as they will, the more people that enter, the more congested it gets, and the more congested it gets, the lower its productivity. And so by keeping people waiting outside, we let the network become more productive. They're able to actually then enter quicker and actually reach their destination at a higher rate. Any questions about that? Excellent. I don't know how much you guys know about MFD-based control. So if all of this is review for you, fantastic. If not, just feel free to ask any questions. I'm happy to take them. But
Vikash, talk about MFD, actually, I'm teaching traffic flow theory class, and in the last lecture, the last lecture of this class, have not gone there, but I will talk about MFD and talk about basically beta model. And I've already talked about the MFD as one network level phenomenon very briefly. So many of the students, but just recent years. Yeah.
Okay, excellent. Thanks.
Yeah,
so that's good. That's definitely good to know. So,
wait, there's a question now.
Yeah, sure.
Siwei asked, we just control to get in, or do we also control the flow to get out?
That's a great question. So basically, if I have a single region, like I'll just say downtown San Francisco, we control the rate that people get in, which, it depends on your point of view. If you have a single region, you're controlling the rate that vehicles get in, and that helps to improve the rate that vehicles are able to get to their destination, which could also mean leaving the network. If I have multiple regions, then, I would like to control the rate that vehicles enter one region is the same as controlling the rate that vehicles exit the region that they started in. So it could be a little bit of both. I'm describing this in sort of a single region context, but when I move on to the actual work, we'll talk about it in a sort of a two region context, in which case we control both entering one and exiting the other one. So I hope that answers your question. So in general, there has been a lot of work on this perimeter metering control problem in the last decade, since sort of MFD was sort of rediscovered, I would say, in the late 2000s. And so since then, there's been a lot of work, particularly in this perimeter metering control problem. But the most common methods to solve this problem require a lot of knowledge about the underlying traffic dynamics. So it requires that we know exactly what the network's MFD is. It requires that we have a model that tells us if this number of vehicles are in the network, here's how many can exit. Here's how the accumulation in the region will update over time. We need to know that information. So the most common method is called a model predictive control approach. I would say it's the state of the art, but it requires that we know this information. There are also feedback-based methods where we say, okay, we just set a point. If the network is this level of congested, if it's more congested, we let fewer vehicles in. If it's less congested, we let more vehicles in. But again, that requires that we know what the MFD is in order to set that point, and we have to pick what that set point is, okay? And there are also there has been one model-free version of the perimeter metering control problem, but it does require an estimate of the critical accumulation or a set point for how congested we want to allow the network to get. So we as sort of traffic engineers have to determine, what is the appropriate level congestion. We don't want more than that. If it's less than that, we want vehicles to enter at a higher rate. But it turns out that information is pretty hard to get, okay? Many studies have been performed to estimate a network's MFD. But if you look at the research literature, there are actually very few studies that actually show a network's MFD, very few. And that's because it's really hard to get that information. You need, traffic flow measurements on almost every link within a particular urban network. You typically also need to combine that with probe vehicle data. So like GPS traces from taxi cabs or probe vehicles. And so there are very few MFDs that have been estimated empirically. And even in real networks, these MFDs are subject to things like scatter. So the first picture I showed, it was like a nice, smooth relationship between flow and density. It turns out at some point, that smooth relationship becomes a bunch of, basically a mess, okay? And there's also features like hysteresis and other things that we can talk about that make estimating an MFD very difficult. So this work, we actually try to use deep reinforcement learning to solve the perimeter metering control problem in what we would say is an entirely model-free way. We're not going to have any input information like what is the network's MFD, or what are the traffic dynamics, when I have multiple regions, how do vehicles move from one region to another? We're going to allow the deep reinforcement learning algorithm to learn all of this and then to give us an answer to the perimeter metering control problem. So the goal is to develop that perimeter metering control method. It requires no knowledge of the MFD and no knowledge of underlying traffic dynamics. And we want this to be stable, meaning the algorithm is able to converge and converge successfully for different types of scenarios. If I have large demands, small demands, MFD with a lot of scatter, MFD with not a lot of scatter, large uncertainties in demands, no uncertainty in demand. We want it to be effective. So it needs to work, but it also needs to be competitive with the existing approaches that, again, require a lot of information. And we also want it to be transferable. We can learn this information in one context and we can transfer it to another context. And it turns out that transferability has not really been assessed in a lot of the perimeter metering control problems that exist in the literature. So to start off with our work, I wanted to talk a little bit about reinforcement learning. And I don't know how much everyone knows about reinforcement learning. I'll tell you that I didn't know much about reinforcement learning until about a year ago, okay? So what is reinforcement learning? In reinforcement learning, we have an agent that learns to make decisions through a reinforcement process. So what does that mean? We have this agent and he is the one making the decisions, okay, about what we need to do. We have an environment, which is the reality, okay, the world that the agent lives in. So every now and then, the agent looks into the world, and receives a state, a snapshot, a bit of information about what's happening in the world, okay? Looks outside and says, oh, it's sunny, for example, what the temperature is. And in our context, how congested the network is. And then the agent makes an action, some action that sort of interacts with the environment or the world. In our case, it's going to be makes a perimeter metering control decision, okay? So he takes an action and then he looks at the environment again and makes a measurement of how his action changed the environment. And based on that, the agent gets a reward. That reward can be a positive reward. If he made a good change, that's great. If he made a bad change, it's a negative reward. But he receives some sort of quantitative reward to understand how well his action worked. And so the goal of the reinforcement agent is to select a set of actions that maximizes the reward that the agent receives, but not just the immediate reward. He looks into the future as well. So he's looking at his current reward and the potential for future rewards. The future rewards, though, are discounted, right? The immediate rewards are worth a little bit more than the potential for a reward later, right? The agent learns by trial and error. So he tries different things, and then he kind of figures out what are the best set of actions. Right? And he tries to do this in an intelligent manner. At first, it's completely random. When the agent is, is just born, for example, doesn't know what's going on, he just picks things at random. But then over time, he learns the results of these actions and starts making smarter and smarter actions, those that will maximize his reward. So it learns in an iterative process, make a change, look at the outcome of that change, try something else. After a while, the trying something else gets smaller and he starts converging towards this is always the best action to take in a given situation. So that's my quick introduction to reinforcement learning. And so how would this work in perimeter metering control? So I'll start with just the simplest case, a single region network. And in a single region network, we don't need to use deep reinforcement learning. We can just do it by hand. It's very, very simple, okay? So let's say that I have this network. This is my downtown San Francisco, for example. I'll just make that up, right? And I have an MFD. So I have an MFD that relates the accumulation, the number of people that are traveling inside the network, with the trip completion rate, how productive the network is, okay? I have this in gray here because the agent cannot see it. He doesn't know that background information. What the agent does see is the state. So he'll pick there'll be a particular state. In this case, I'm supposing it's a congested scenario. And given that state, he sees how productive the network is. He says, okay, there's this number of vehicles in the network. it's this level of productive. And then the agent will make a decision randomly. So maybe the agent says, you know what I'm going to do? I'm going to let more people into this network. I'm going to lower the restriction. So I kind of like drew this as a gate here. I'm going to open up the gates and allow more people in. If the agent lets more people in, well, what's going to happen? Well, the accumulation will get higher. And if the accumulation gets higher, unbeknownst to the agent, what's going to happen is we're going to kind of move this way on our MFD, and our productivity is going to go down. So after the agent does this, he'll learn that, oh my goodness, like the productivity went down. That was a bad action. Okay. And then he'll decide, I'm not going to do that anymore. Likewise, if we repeat this process, so I'll erase all this stuff. If I repeat this process, maybe the next time the agent says, okay, at this particular state, I'm going to let fewer people in. If I let fewer people in, I'll get a higher productivity and I'll get a higher reward, and that's good for me. Okay, so in a single region, it's very simple to see what the answer is, right? We can try this on an uncongested scenario. The same thing will happen. If the network's uncongested, well, if I let fewer people in, then I actually get a lower productivity, and so that's a bad thing. I won't want to do that anymore. If it's uncongested, I want to let more people in so that the network becomes more productive. And so if we do this over time and try this at different states, the agent will eventually learn on his own what to do when the network is congested and what to do when the network is uncongested. And the idea would be to try to drive the network towards this maximum productivity state. But again, it doesn't require that we have knowledge of what that MFD is. We don't need to know the functional form, the curve. We don't need to know the traffic dynamics. We don't need to know any of that. It's just through a trial and error procedure, okay? Now, it's an intelligent trial and error procedure, because if it was purely trial and error, it would not be very smart. At the beginning it is, and then based on those random actions, the agent gets smarter and smarter. In a single region, very, very simple. In two or more regions, the dynamics becomes a little bit more complicated. These are the equations that represent the dynamics here. And so this is what we tried our deep reinforcement learning agent to do. We looked at a 2-region network. Okay, here are the dynamics, the MFDs. This is kind of what, the background information. The dynamic equations and the MFD were known when we did the numerical situations by us, but it was not known to the agent. The agent had no information about what was going on, and it was its job to learn it. Okay. So here's just a little bit more information on the MFDs that we used and things like that. We made one region bigger, one region smaller. None of that is terribly exciting or interesting. The key here, though, is this is what happens when we don't let the agent do anything. If we said, if we did no control whatsoever, region 2 got very, very congested. Region 1 got very, very uncongested. And region 2 was the middle, kind of like the downtown. And because it got so congested, it was not a very productive network. Okay. So we did that, so that's kind of the setup. Now, we had all of this information in the background. This was sort of representing our real world, but the real world is pretty messy. And so this is what the messiness of our real world looks like. We knew we had like average demands, like as if we were like forecasting what the demand would be, but the real demand on any day, on any time period, had some errors associated with it. So you can see here, for example, this top line represents the demand for a particular set of vehicles going from, in this case, going from the outside region to the inside region. But during any single day, that demand fluctuates, and it fluctuates considerably, actually by quite a lot, up to 33%. Okay. We also had errors in the MFD, and this, I think I showed you a picture of two of different MFDs. On the left-hand side, it's pretty nice, well-defined. You can draw a line through it, no problem. On the right-hand side, it becomes a little bit more chaotic, and there's a lot more uncertainty. Okay, so that represents our sort of environment. And we had a couple different deep reinforcement agents that we were dealing with. The first was a discrete agent that used only discrete action spaces. So in this case, we had yeah.
There's a question in the chat.
Oh yeah, sorry.
From Peñon. Oh, it just popped up. So if you don't consider the network, how will the reinforcement learning procedure could estimate, how the reinforcement learning procedure could estimate and get the reward, the flow rate fluctuations based on the input density?
Yeah, that's a great question. So basically what I'm saying is like, we did some numerical simulation, that represented our environment. We knew all of that information. We have to program, in a computer simulation, we have to program everything. So we have to know what that stuff is. But then we kept the agent separate. So the agent didn't see any of that stuff. The agent only would get the state, which was the estimates of density, or in this case, accumulations and some of the demand information. And then after some time, after making an action, we would return to the agent the level of productivity. That can be measured in a couple different ways. In our simulations, we gave it the actual productivity values, the trip completion rate. In reality, it's just really a measure of the average flow. They're essentially synonymous. They're proportional to each other. Higher average flows, higher trip completion rates. It would basically be the same thing. So that it's measurable pieces of information. I was just trying to emphasize that the DRL agent didn't have access to any of those dynamic equations, didn't have access to the MFD. It just had access to the results of its actions. So hopefully that clarifies.
I have a follow-up question maybe.
Yeah, sure.
So how often are you feeding the agent with information? Like when they do an action, how much do you wait to measure the next state? Or
that's a great question. We can make it whatever we want. We can pick whatever sort of time interval that we want. I think in our simulations we did on the order of, it was either 1 minute or 5 minutes, okay. Right? And that's just because we've never done this before. We haven't looked at the sensitivity to the how long between actions. We can certainly try that. I think in most perimeter metering control problems, they use control intervals of about 1 minute to 5 minutes has been pretty typical in the research literature. In practice, I think that's probably too fine of a resolution, and it would probably be like 10 to 15 minutes. I think would be more realistic.
Okay, thank you.
Yeah, it's a great question.
More questions.
Yeah.
CY says, how do we usually get the trip completion rate from empirical data?
That's an excellent question. We typically, empirically, to get trip completion rate, we typically have to have some sort of probe vehicle data, some sort of GPS trace type data. So in other empirical studies, that has typically been like taxi cabs, fleet vehicles that are always reporting their location. And we can use that information to infer or estimate the trip completion rate. For the purposes of this work though, just in the MFD literature in general, the trip completion rate tends to be, if we assume that trips are more or less the same length, which, during a given peak period, that may or may not be true, but if it's true, then the trip completion rate is proportional to average flow. And so we can just measure with loop detectors what the average flow is on a network, and we can estimate pretty well what the trip completion rate is. And we don't really care what the number of the trip completion rate is. We just need to know, is it high or low, or is it getting higher or getting lower, right? So the actual number, I think, is not very meaningful. It's just, are we sort of approaching a maximum or not? So hopefully that helps clarify. So in our work, we kind of had two different types of agents. One used the discrete action space. So it took the set of control actions. This value U represents U of 0.1. It means like we're kind of closing the borders as tightly as possible and not letting people go in between the regions. A U of 0.9 means we're opening the borders and they're moving back and forth kind of like at their will, okay? And so in our first case, we discretized that. And then we said, okay, given what the current state is, we can either increase it by 1 unit, keep it the same, or decrease it by another unit. It's not very interesting. It turns out this was really initial in our work, and it didn't really work very well. It worked, it just didn't work very well. We also tried a continuous agent, in which case we had the entire space to play with, and the agent would just pick what number along this continuum. It turns out that worked much, much better. And so most of the results will focus on that. So what we wanted to do was compare basically the following scenarios. A no control case where we just don't implement any sort of perimeter metering control. It turns out that's just bad, okay? And it's not a surprise. This is pretty common in this type of, these types of setups. It's designed to be that way. We tried the model predictive control approach, The model predictive control is basically the state of the art in this perimeter metering control, but it does require that all that stuff that I said we didn't give to the agent, the MPC controller needed to know. So it needed to know what the MFD was. It needed to know what the traffic dynamics was. And then it basically determined the optimal control to do at any time step. And then we compared it to our two agents, our discrete agent and our continuous agent. And so I want to talk a little bit about the results here. I think I'm doing okay on time. So we tried that for different levels of uncertainty in the MFD and uncertainty in the demands. So this is the case when there is no uncertainty. The demand was always constant. There was no fluctuations, and the MFD was perfect. Even though we didn't know what it was like a line, a function with no error. Okay. Sure, I'm showing a lot of different information here. So the gray line is the no control. It's the cumulative number of trips completed. So basically how well the network is operating. The gray line is no control. The orange line is MPC control. And the x-axis here is time. So how quick, after how long, how many updates of the agent, because the agent is constantly learning and updating itself. So the no control case, it's independent of how well the agent learns. The MPC case, independent of how well the agent learns. The green line is our discrete agent. So you can see our discrete agent starts and he's doing a pretty bad job, right? At first, the agent's pretty, for lack of a better word, it's dumb. It doesn't know what to do. And so it just makes random decisions, right? And then it keeps making random decisions. And after some time, it starts to learn that some decisions are better than others. And when it starts to learn, the performance improves, which is good. It improves. And then it starts converging. It says like, I can't improve anymore. Okay. This is the best that I can do. And so the thing that I wanted to point out is that the discrete agent, it sort of like approaches the MPC, but it's never as good as the MPC. It's still a little bit worse. And that's because we're purposefully, the MPC has a continuous action space. The discrete agent by its nature has a discrete action space. It will never be as good. The blue line is our continuous reinforcement learning agent. And you can see it starts off really bad. Like the first day, it does a horrible job, like worse than no control. It's just randomly guessing, but it very quickly learns what to do. And once it starts learning, it learns fast. And its performance improves over time until it eventually converges. And if you can see here, I kind of drew all over it. I'll erase that now. You'll see that it not only improves, but it improves to be so well that it performs better than the MPC, even though it doesn't know all of the dynamic equations. It doesn't know the MFD. It doesn't know any of that. It actually outperforms the MPC control. The fact that it outperforms it, is not terribly important. It basically does as well as the MPC control, which knows everything. Our deep reinforcement agent doesn't know everything. It just learns by trial and error. Okay. Now we did this many times under different environments, different uncertainties. This is what it looks like as I go from the left to the right here. As I go from the left to the right, basically I have more error in the MFD. And as I go from the top to the bottom, I have more error in the demand. So I have less confident estimates of what the actual demand is. And you can see that this is very, very consistent. What happens is the no control case is bad. The MPC case is really good. The green line, which is our discrete reinforcement learning agent, does okay, right? It takes a long time to learn, but when it does okay. And our continuous agent learns really fast. And it actually does as well, if not better, than the MPC. Again, not knowing anything about the network, anything about its dynamics, anything about the MFD. Okay. When we look at what's actually happening, so we look at sort of how the network evolves over time, right? Before, I showed these pictures before. Again, the same colors are used. So gray is no control, orange is MPC, blue and green are our agents. You can see that our agents are sort of mimicking the behavior of the MPC, right? It's doing about the same thing compared to the no control case. And the agents are learning these kind of highlighted lines here. These are what the critical accumulations are. It's learning what these critical accumulations are that maximize network productivity and keeping the network there. It's trying its best to keep the regions at their critical accumulation, the ones that maximizes its productivity. So this is a summary of the results, more just a numerical summary. We did this again with just different metrics. Now we're looking at, again, a cumulative trip completion. The key points to say here is that the no control is red. It does a lot worse than any of the other methods, okay? When I compare the MPC with our discrete agent does about as well, just a little bit worse, on the order of like 1 to 2% worse. And when we compare the continuous agent to the MPC, our actual continuous agent basically does either about the same or better. So on the order of like 0% difference to like a little bit better in terms of how many vehicles can get to their destination. So we tried this on one scenario. Great. What does that mean, right? So we tried it then on a bunch of different scenarios, and we tried it in scenarios where we know the answer. So this previous scenario, if I have like a 2-region control problem, you know, where one network region is congested and they're all kind of congested, we don't really know what the answer is. So we tried this in scenarios where we do know the answer. So the first thing we did was we repeated this entire experiment where the entire network was uncongested. There's no congestion whatsoever, right? Congestion will never develop. It will never arise. In that case, the optimal thing to do is nothing, okay? And so what we wanted to know is, could our agent learn to do nothing? And so the results that we found was, yes, it could. We tested this, and over some number of iterations, our agent was able to learn, and fairly quickly, that the optimal control scenario was to do nothing and match what the MPC did. And we confirmed that the MPC also did nothing. We tried it in a very congested scenario where everyone was going from the outside to the inside. And in that case, the optimal thing to do, which we know, we didn't need an optimization or anything, we just know is to close the gates. Just stop, don't let anyone enter the congested area. Just keep it as, keep people on the outside as much as possible. And again, our agent was able to learn that that was the optimal thing to do. So it works on situations where we don't know what to do. It works exactly how we would expect in the situations where we do know what to do. So I think that's pretty nice. And then the last thing we did was we tried this. We said we trained the agent in one set of scenarios, and then without retraining it, we just took that agent and applied it to another scenario. Okay, that would be similar to like, I trained this agent in downtown San Francisco, and then I'm going to go to New York and say, okay, I want you to work, do you work in New York City as well? Okay. We tried that for different starting accumulations, different demands, different MFDs, so different errors in the MFD. The pictures here are not terribly exciting. All I wanted to say is that basically the lower the curve, the better. So this is total, we switch our metric here to total travel time. So gray, you can see the gray line has the highest travel time, and then MPC and our blue reinforcement learning agent is always doing better than the no control case.
Excuse
and so,
me?
Yeah.
There's a question in the chat.
Oh yeah, what's up?
From Shimon. Before reaching the ideal condition, is it possible that this step is worse than the step before? For the previous example, it is possible that the change of the lower productivity value than before, and if there is a non-concave fundamental diagram.
Yeah, so I think there's two different questions, right? But basically, is it possible, before reaching the ideal condition, is it possible that this agent does worse over time before getting better? Is that the question? I think that's what the question is. And I guess the short answer is yes, absolutely. And I can show you an example of this. So here's our training curves. And the solid lines here, I didn't go over it in a lot of detail, but the solid lines kind of represent our median operation of a set of agents, okay? And what you can see here is that, like, I'll just pick this line here. So I'm going to focus my discussion right here on this picture. What I'll show you here is right here, the agent's getting smarter, smarter, smarter. And then at some point it starts getting less smart, right? It does a little worse. And then it gets better, and then it gets worse, and then it gets better. And so like, it's converging. On average, it's getting better, but like, on a given day, one day might be worse than the day before, okay? That is actually pretty typical of reinforcement learning agents. And part of the reason is the agent is converging towards an optimal solution, but while it's doing that, it still wants to explore. It's saying like, I know I'm doing well moving in this direction, but what if the real optimal condition is behind me? I should still keep checking. And so it's like searching all over the place. It's still tending to search in the right direction, but it's also searching randomly. And that's related to, I think it's a great question. And it's related to something that I'll get to, well, I guess I can just mention it now. We're also now doing experiments on how to make this learning process better, more efficient, and keep the agent from like guessing unnecessarily, okay? Because then one drawback of this is like, if I were to implement this in a real city, the first few days is actually worse than no control. So if I go to New York City and I say, hey, give me 100 days and I'll fix your traffic problems. But guess what? Like the first 20 days, things are going to be way worse than they are now. They'll just laugh me out of the office, right? They'll say, get out of here. Like this is, you know, I don't care if it's going to be better in 100 days. If you make things worse tomorrow, you're in trouble, right? So they'll never let that happen. I guess a spoiler alert, like we have found methods to ensure that our method is always better than the no control case. So that if I did go to New York City, I can say, look, our agent will learn and it will do a great job in time. And in the interim, it will still do better than you're doing right now. So we've kind of done that. We're calling it like a human guided deep reinforcement learning. And it's basically by combining some of our knowledge with the agent. So in this presentation, the agent's doing all of the learning itself. In that, I guess it's like a follow-up work. We're telling the agent, listen, like I know a little bit about this. Like, trust me, don't search in that direction. There's a reason for it. And so that's what we're doing now. But I think that's a great question. I think there's another part to the question that I forgot now. Oh, what if there's a non-concave fundamental diagram? That is an excellent question because I'm doing work right now that's sort of proving that we should expect non-concave fundamental diagrams to exist. And the answer is, I don't know. We have not tested that on a non-concave fundamental diagram. I think every single perimeter metering control problem that I've ever seen assumes a concave fundamental diagram. I disagree with that assumption, but it is sort of the standard practice right now, based on everything we know empirically. But those are great questions. So I'll skip over this part. It's very, you know, just to save some time for questions. I guess the short answer is, it is transferable. When we take our agent and we apply it to a different scenario, in most of the cases, it works better than the no control case. And in many of the cases, it still works as well as the MPC, even though the MPC needs to know a lot of information. So to summarize, our model-free deep reinforcement learning appears to work well to solve the perimeter control problem with two regions. The methods developed using both discrete and continuous action spaces, although the continuous space is much, much better than discrete. Our methods are stable. They always converge. They're effective. They're basically comparable, if not better than the state-of-the-art MPC, even though the MPC knows too much. And they're transferable in that we can take it and apply it to a new scenario, and it actually works pretty well. In terms of implementation, we can basically use surrogates for the information that we're sort of assuming that we know. I think a great example of that is the trip completion rate. You know, one of the questions was, how can you get that in practice? And there are ways to do that, although I would argue that it's very difficult to do. We actually don't need that. We can just use average flow, and average flow is actually a pretty easy gettable thing. And then in terms of implementation, you can also develop this in a simulation environment and then just go ahead and apply it because we know that our agents are fairly transferable. So with that, I'll just say thanks. And if you have any questions, I'll be happy to take them.
Okay, thank you. Thank you for keeping this very timely and short. Are there any questions? You are all welcome to unmute yourself if you want and ask. And while people are thinking their questions, I have one.
I just saw Dr. J, so I just want to say hi to Dr. J real quick. Hi, Dr. J.
Hi, I was about to say hi to you because we haven't seen each other since, when was it? ISTT to Chicago, right? The last time
in
we
Chicago. Met. Yeah, so I apologize. I didn't mean to interrupt, Irene. I just wanted to say hi to Dr. J before I forgot.
I missed the first 10 minutes, but it was this was a wonderful talk. It was just stuck to the core of the topic. It's so nice.
Thank you.
thanks for doing it.
Yeah. Okay. Thank you, Vikash, for the great talk. And this is really a timely topic. And I believe many of our students are also interested in reinforcement learning, and some of them have taken some classes. Even though those classes, I heard that the machine learning, those artificial intelligence, those courses are really popular and hard to get in. But there's a lot of interest, and this is really a timely approach. And I have one. I have a couple of questions. Maybe I will ask first one regarding the reinforcement learning. I also just started to learn about it with one visiting student from China, and we learned that the choice of the reward function is very, very important. So I'm wondering, could you please share some of your experience? Because we learned that, with a different reward function, the convergence speed or whether it converges and things, would be impacted quite a lot by the choice of reward function. I'm wondering if you have any comments or any, thing that share.
Yeah, so I think that's a great comment. I mean, great comment / question. It does matter. It is very sensitive. So I've also worked on deep reinforcement learning applied to, for example, a single isolated signal traffic control, right? So, I have a signal, I have left and right, I have up and down. Let's just say there's two phases, left and right, up and down, okay? If you pick that reward function poorly, where there's not a really good relationship between the action and the reward, then the agent takes a long time to learn that relationship. And so what I mean by that, and why I bring up this single intersection example, is when we were doing that, our first reward was travel time. We said, look, we want to minimize travel time. Okay. I mean, that's what we wanted. That's our goal. That's our job. Right. I was working with someone in like computer science, and they said, well, what do you want to do? You traffic people. And I said, we minimize travel time. What we found was that's actually a pretty poor reward in deep reinforcement learning, because if I have a vehicle here, right, far away from my intersection, and there's just one vehicle, that travel time doesn't matter if I change the traffic light until that vehicle gets to the intersection, because if it's far away, I can change the light 100 times before that vehicle gets to the intersection. That travel time is there. That's the free flow travel time. We cannot reduce that. Okay. So our agent would just like try all sorts of things, and this vehicle's approaching and it would say, I don't know what to do. I'm not making a change. Right. And so we have to pick that really carefully. And so in that case, we actually did some like derivations to understand what is the appropriate reward that we can map that, the change in the action to our eventual reward, travel time. In our case, it was queue length. We want to minimize the queue length. Yeah. We found that by minimizing the queue length, we can minimize the travel time, but in a way that it directly relates between the action, the reward, and our overall goal. Okay. Yeah. And so you have to kind of think about that very carefully. In the perimeter metering control problem, it was trip completion rate in the next time step. That's actually not our overall goal. Again, our overall goal is travel time. We want to minimize travel time. We had to do a lot of tests and a lot of derivations to get to that point that travel time would be minimized by maximizing the trip completion rate at any point in time. And so and that has a very direct relationship between action and that reward in a short-term case, so that you don't have this situation where I change the action and my reward, I get no real relationship with the reward. And we learned that from the single intersection, because again, a vehicle far away, I can change the signal 100 times. It does nothing to that travel time if it's a free flow travel time. It will impact the delay, but how do I define delay in a signal context, where I have to measure things on the roadway and things like that? And so I think that's a sort of a great question, and that's how we solve that.
Yeah, this is great. And actually, when we learn about, reinforcement learning or artificial intelligence, sounds like a black box. Our domain knowledge is no longer relevant. But from your experience and our experience, it just shows it's totally opposite. Our domain knowledge is still totally relevant. maybe not in designing, the control method itself, but in choice of reward function. I mean, the domain knowledge, the insights definitely are highly relevant.
Yeah, and I think basically trying to relate that overall outcome, travel time, minimize travel time, to a short-term outcome that is related to the actions. I think you can't really do that well without domain knowledge.
Yeah.
As another example, this computer scientist that I worked with, they came to me and said, hey, we're interested in, we've been doing this. I want to show you this thing that we did. And I said, awesome, let's look at it. Deep reinforcement learning, signal control. And they showed it to me and I said, fantastic. And I said, well, how does it perform, with like a fixed time controller? And they said, we don't know what that is, It's like, okay, no problem. And so I wrote, I literally just wrote on the blackboard. I said, why don't you try that same scenario with this fixed time controller? Yeah. And I beat their deep reinforcement learning algorithm with a fixed time controller. And they're thinking like, well, this guy is like magical, and it's like, no, I just know about traffic signal timing. And so if you don't have that domain knowledge, you think you're doing a great job, and it was working to some degree, but it wasn't really achieving its actual purpose. And so I was able to write out in 30 seconds, Webster kind of formula. Here's what the splits are. Let's try a fixed signal timing with this cycle length. And I beat their super smart algorithm. Does that make me smarter than a super smart computer? No. I just have a little bit of domain knowledge. And then by combining that bit of information, we were able to do so much better. So no, the domain knowledge is incredibly important.
Yeah, great.
Okay, there are questions popping out in the chat. But maybe I have a question in these lines of domain knowledge and not, and maybe I'm putting myself like in the, well, maybe a bad questions, but if you're implementing this in real life, you're actually measuring the density or the state, right? So what benefits do you think it's having this reinforcement learning agent versus, since you can measure the data, do some simulation or pre-application analysis and calculate the fundamental diagram, because the MPC was doing very well. Like maybe the difference was so small that why don't you do the?
I agree. So I completely understand the question. The question is, if this thing is learning by measuring on a day-to-day basis, why don't you just do those measurements, get the MFD, and solve the problem? I think that's a great question. What I will say is getting that MFD, is the actual functional form of the MFD, is difficult. It requires, anyone who's ever tried to do it, even on a simulation platform, it is not like where everything and you can output everything. It is not straightforward. Ideally, what you need is the trajectory of every single vehicle traveling in that network. You're never going to get that, right? Okay, so you can combine loop detector data with probe vehicle data to get that. Great. But that probe vehicle data you're going to need over the course of several days. And if you're using taxis, do taxis actually represent other vehicles? Maybe, maybe not. You can make a case that they do in some cases. You can make a case that they don't in others, right? So it still requires a lot of work, and it is a lot of manual work. Whereas I can argue that I think our method can work well detectors only without requiring probe vehicles, potentially, okay? That being said, if you were to spend all this time and energy and effort to estimate the MFD, apply it onto this, use the MPC, then you are stuck. You are stuck using that MFD. And what I think you can find is that local traffic changes can change the MFD. It can change its functional form. If I take a street and I retimed its signals, now the MFD changes. The MFD is supposed to be demand independent, meaning it's not a function of the demand, but actually it is. It really is. And so if the demand patterns change, the MFD will change and will adjust. And if I'm using an MPC-based approach, I don't know how it's going to change. So I'm stuck with a model that represents reality that may not represent reality anymore. I'm optimizing based on this model, and now the world is behaving a little bit differently. If I'm using a reinforcement learning approach, I can have this model converge, and it can keep learning over time, and it can actually learn that my actions aren't actually working anymore. Let me start adjusting them again. And so I do think that sort of self-reinforcement over time is probably a better way to go, because then you don't have to go and calibrate and re-estimate the MFD every single time there's a change, right? Now, that's a little bit unfair because, macroscopic phenomena should not change significantly when there's small local changes. So in some cases it won't. But if I have, I don't know, let's say that I'm in downtown San Francisco and now we're doing maintenance on several of the roads. Closing off roads for maintenance can cause a very drastic change in macroscopic performance. If I estimated an MFD and I'm using an MPC, now I have to go re-estimate that MFD during the work zone time, which no one was going to want to do, time intensive, data intensive. In the meantime, my controls aren't working well. In a reinforcement learning approach, you say, okay, go do the work zone. And then while this is happening, our agent will, maybe the first day won't perform very well because it's using yesterday's information, but the second day it will now integrate that new information and keep integrating that new information over time smoothly until things get better.
Okay, thank you.
Yep.
Maybe a follow-up question to Irene's question. I mean, another thing is that we notice, this reinforcement learning could take a pretty long time, to train, to learn about the situation. I'm wondering, I understand that for this kind of a network level control, it does not have to be that responsive. But I'm wondering if computational cost could be an issue here at all. But I've seen some, you might know that, Alice Bayan, they've done some, traffic, this, link level, say, platoon level control. I suspect for, in those kind of cases, the computational cost could be an issue such that it's not responsive enough. So I'm wondering if this could be a concern in this case.
Yeah, for like a network level problem, I wouldn't really be that concerned about computational costs. I mean, we did this on a PC and it works. And so I imagine if we were to do this for an entire San Francisco, first of all, we can have like a dedicated server or something like that. I mean, for a platoon level problem where you're dealing with individual vehicles, that each of these vehicles need to be running these algorithms, that's a tough situation. But related to the convergence time, I mean, if you look down here, these training iterations, you can consider that as like a day. Right. Okay. And so you can see that in some cases, like with the discrete agent, it takes like 100 days before this thing even starts to learn. Like that's not good. I mean, I'll admit readily. Our blue guy, our continuous agent, he's working well, and within like 20 days, he's doing pretty good. So that's reasonable to learn within 20 days. But what I will say is that Dongchen and I have been doing some work to combine our human knowledge with our reinforcement learning agent knowledge. So that basically what we're finding is that we can take this bot, that first day's performance, we can improve it significantly. And it's possible that we can get this thing to converge even faster. And so, in the order of like a week or two. And if that's true, well, goodness, like that's all we need. We need it to start. We need it to start better than the no control, right? Because I will readily admit, if I took these results to a city and I said, I can do great for you 50 days from now, but tomorrow everyone's going to call for your job, they'll just laugh me out of their office, and they should, right? Like that's doing worse than no control is not an option. And that's what happens here. It does worse than no control. Okay, we can improve that lower bound performance just with a little bit of human knowledge. And then if we can get it to converge faster, I think this is implementable. And that's what we're doing right now. And we have some preliminary, I didn't put it in the presentation. We have some preliminary results that basically show I could basically take this blue curve, I can move it up here. Right now, if I did that, it would actually take longer to converge because the agent wants to like search in all different directions. And we're just trying to tell him like, hey, stop that guy. Like, just focus on what we're saying. But we're trying to like delicately balance between how much I tell it what to do and how much it does it on its own. If I tell it too much what to do, it's not deep reinforcement learning. It's Vikash's, perimeter metering control, and that's not useful either. So we're trying to balance between that. I think we're on our way there, but I think it's a really good question. It does take time, but I think we can make this within the scope of being able to be implemented within a couple of weeks.
Yeah, I think that's great. I mean, when we design the control strategies, I think you've been considering all these constraints. All these important constraints, those needs to be considered when we design using whatever new technology it is.
Absolutely.
That's great. Yeah. Thank you.
Thank you.
Okay, and let's go for the questions in the chat. Jimin, do you want to video yourself or?
Okay, thank you, Irene. Hello, Professor. I have a further question about the convergence pattern. Things like I find that you did experiment for a long time, even after the results are convergent. So is there some way for us to define the convergence point? Means that is there any symbol for us to say, oh, that we get the optimal result and we can end the experiments to make the simulation, or say to make the detection more efficiently?
Yeah, that's a very good question. I would say for the purposes of this study, we set our convergence criteria to be extremely strict. And the reason why we did that is we didn't want to cut off the agent from learning too quickly. Okay. So I would actually argue that we we made it so that the agent would never really officially say that it was converged, in the sense that we wanted to see if it can ever just keep getting better. And it didn't. You can see that all of these blue lines converged, after about, I don't know, like 75 to 100 days, it's basic, nothing's changing. Okay. So you can select the convergence criteria to whatever you would like. And we selected extremely strict criteria because we know this is a research study and we're trying to examine every aspect of this problem. In reality, I think you can probably be a little bit more relaxed with that convergence criteria, because you can see that after some time, things are really not improving. It's just sort of fluctuating. And a lot of this fluctuating is happening because the actual world is random. And so, you can do the same thing, but if a different day has a different demand pattern or the MFD is a little different, you'll get a slightly different outcome. And that's part of the reason why you see that fluctuation and sort of a lack of convergence in our case. I guess the short answer to that question is, how do you define a convergence point? You can pick on whatever criteria you want. We looked at moving averages of the outcomes, but we also looked at the parameters of the deep reinforcement learning agent. We looked at these neural networks and said, are you still updating these links in the neural network? If you were, we said you weren't converged yet, right? Now, what does it mean to still be updating? It was making like microscopic changes, but we just let it make these changes just in case to see if we can do a little bit better. It didn't really make any outcome. So we could have relaxed those significantly and it would have converged pretty fast. We just wanted to see what these curves would look like for the length of the time. Okay, thank you, Professor. Yeah, that's a good question. And that's more of like an implementation question. And since we're not implementing yet, we just wanted to see like how well, what can this thing do? And then I see another question. Do we need to worry about collision-free or spillback issues in this study? So this was done entirely in a numerical simulation. And so we didn't use like a micro simulation or anything like that. And so we didn't have to worry about individual intersection control. One of our next steps is to sort of combine a local level controller that controls every single intersection with a macroscopic controller that's telling sort of the global picture what to do. And then we'll have to consider things like spillback and stuff like that. And that will be trained in a micro simulation environment. In this case, we did numerical simulations. None of that was of a concern to us. But that's definitely something that would have to be taken into account before something like this can ever be implemented.
Now that you go back to the intersections, so I have a question. Oh, sure. Go for it.
I guess because if you're talking about the training iterations, basically look at it as day by day, right? Is there any way to make it within a day? I mean, can we, I know that the demand patterns and everything, it changes day by day, I suppose, and that's probably the reason why you have to do it that way. But is there, can we just, do 2 or 3 iterations for a day, or maybe split up the network into pieces where they all learn from each other or something like that? What happened for the first hour? Some learning, and then they talk to each. I don't know. I think that's a great. I think that's a great question.
the learning has to be done on like a repeatable block. And in our case, our block was a block of time representing a morning peak hour.
Yeah.
And so like, we're looking at the entire morning peak hour and the decisions made over that hour. And then, or, I think it was more than 1 hour, but just the peak period, right? And so today there's a peak period. We learn about that to implement for tomorrow's peak period. We learn about that to implement for the next day. So that's why we consider it day by day. We're also looking at sort of multi-region control. So
Yep.
this time we had two regions, two regions, one interacting with the other. Now we're looking at sort of multi-region control. If we have like 10 regions, can we learn information about these two regions and then inform what's going on here? And it turns out that is sort of related to what you're talking about.
Yeah.
Yes, we can learn about that a little bit more. And so, yes, we can learn about that more over time. In the single intersection control problem, like just a single intersection, it learns much faster in terms of like length of real time. It's longer in terms of like iterations, but each iteration is like one cycle, let's say. And so in a day, you have hundreds of cycles. And so after a day, you can kind of learn everything that you need to know. The problem here is that a cycle is a whole morning peak. And so we have to like exhaust those morning peaks to learn the overall outcomes. But I think there's ways to get around that. And like I mentioned, like learning from one pair of regions. If I have many regions, I can learn from one and instantly apply that to another one. I think it would make it faster.
Yeah. Okay. Yeah, that's what I was thinking. Changing that temporal aspect to sort of the spatial repeatability or something, right?
Yeah, we're doing that. So what we're doing is we're looking at like, can we have one controller that's learning from multiple regions at the same time? So like each morning we actually get like several bits of information, several trials, like 10 different trials. And so it kind of speeds up the learning process. It also slows down the learning process because it's a much more complicated problem. And so we're trying to balance that. So we're looking at that, Dongchen is looking at that multi-region. He's working on a couple of different things at the same time, the multi-region and the human guided knowledge, and both of them are showing some promise.
Yeah, okay.
Great. Are there any other questions?
I thought, Irina, you had a question. No,
yeah, but actually, after thinking a bit more, I kind of answered it myself, but let's verify the answer. And so I think that traffic signals are working more like a discrete control rather than the continuous. You compare the blue and the green, and because there's a fixed red time or green time, the amount of flow that you can let, it's kind of somehow discrete. But then I thought that because it's a whole region, you can average out many intersections and then you can make it continuous, almost continuous.
Even at a single intersection, you can sort of treat it as, it depends on how you sort of view the intersection, right? You can treat it as a discrete if you say, look, I have this amount of a cycle, and then the green time can be 10 seconds, 12 seconds, 14 seconds, 16 seconds. That's a discrete representation. If I have this amount of, if I can say, okay, this is my cycle, and the green time can be 10, 10.001, 10.002, which functionally means makes no difference, right? But at a single intersection, it makes absolutely no difference. But then on a macroscopic level, it can certainly make a difference because I can provide 10 to one intersection, 12 to the other, and I could get the outcome as something in between. So I think that the continuous agent would work there because of, I think, for that reason.
Yep, makes sense.
Okay, maybe I can ask another question. So with this kind of parameter control based on reinforcement learning or any other methods, then the drivers, the passengers could change their travel pattern. That is induced demand issue in transportation. I'm wondering, do you guys have planned to evaluate the potential impacts of this could induce some demand or suppress some demand or change their demand pattern totally and things like that?
Yeah, so in our multi-region control problem that we're working on now, we're not considering people not traveling. So we're not considering the choice of whether to travel or not, which I would say is more of like the total demand. But we are considering route choice, because in a multi-region network, you might, like if I'm going from here to here, I can go directly, I can go up and around, I can go down and around. So I have a lot of, and if I make a control decision, it might change how people reroute. And we're certainly considering the route choice component to that. But we're not considering like, okay, like it's congested today, I'm going to stay home. We're not considering that. We can probably, I think one step at a time. The current problem is pretty tough. In the two region control case, it's not, there's no route choice to really consider. We can add a demand choice to it. We just haven't done that yet. Shooting's working on something else with me that we're looking at, sort of how people travel or choose not to travel under different perimeter metering decisions. And we're kind of looking at that. I think it's a good question. We're just not considering it in this problem.
Okay, cool. Thank you.
Stop my share now.
Yeah, maybe I would like to ask you, I don't know if I talked to you regarding, my view on the MFD versus beta model. I don't know if you heard about beta model, the relationship.
Yeah.
Because I think MFD is a misnomer for the type of model that you are using, which is a dynamics model, right? It's to describe the dynamics in a road network, while MFD is just a very important component, but just one component of it. So just like, the relationship of MFD to this ODE, the dynamic model, is just the same relationship between fundamental diagram, traditional fundamental diagram, and the LWR model. So, I mean, we never call the LWR model as a fundamental diagram model. There's a place to study fundamental diagram model, but we should not call LWR model as a fundamental diagram model. So I talked to a number of colleagues, and they tend to agree with my my point on this one. I think that is a misnomer. And from you guys, I mean, Daganzo's 2007 paper with the ODE model actually is the first among the Berkeley School to propose such a dynamic model. With MFD as an important assumption of it. So basically assuming a network level flow and density relation. So I think this view is very important to have this network, consider network as one single reservoir, as Daganzo said, or a single neighborhood, or this kind of level model. I think this is a great idea. So I think it is helpful to clarify the basic the basic concepts and assumptions behind it.
Yeah, I think that makes a lot of sense. And I mean, I think I tend to use MFD based, or regional traffic control model. I think that, to me, it's a terminology. It's the MFD. I don't sort of use the term MFD model, because I agree with you. The MFD is a relationship. It's not, a relationship is not a model. What you do with it. So Daganzo's paper in 2007.
It is a model, but it's not dynamics model. It's just a flow density relation. But it does but to be able to get to this ODE model, we need other components. Just like in the LWR model.
Yep.
Yeah, I tend to agree with Wenlong on that. I think especially when he brings up the LWR, the model, that we don't call, that to be the fundamental model. So
even we don't call LWR model as fundamental.
That's an argument. Yeah. So I think there's something behind what Wenlong is saying. I think people just use things wrongly. Not in your presentation, because like you said, it is MFD based. Which makes a difference. It's not an MFD model or anything like that. It's MFD based. MFD is important by itself, but I think people just kind of, we see this everything becoming a mishmash.
No, I agree. I absolutely agree with that.
And also now you know that MFD, I mean the empirical results, I mean there's a result already back in 1969, and the assumption were already available in several other studies, even Ken Small 2003, and and more importantly Vikash, he had, but it's unpublished. but now you was edited and published just this year. So I feel Vikash view is more complete, by including considering what kind of assumptions are needed to derive such a ODE model for the network traffic flow. I think that is another thing I noticed that the idea also starts from Vikash. Actually, Vikash, you commented that now in this model we do not care about where the vehicles are at each moment, on which street, which location. That is that is spot on. But there's still a space dimension behind it that is relative to the trip distance. So actually, Vikash explicitly show that when the trip distance follow negative exponential distribution, then we would be able to have this ODE model. And so I think it will be helpful for the whole community. I know you are one of the pioneers and have been working, have made a lot of contributions in this area. So
yeah, no, I agree with you, and I especially that negative exponential distribution, because I think with the ODE model, it actually violates the directly violates the fixed trip length discussion, because vehicles have instantaneous travel time. It's impossible for that to work, and so the boundary conditions, or the startup, and then the sort of like the slow it requires, again, DeGonzo's paper, he called it slow varying traffic dynamics, which I think is just a way to sort of wave his hands and sort of ignore some of these issues. But I think having that backup with the negative exponent, I think that actually makes a lot of sense. It actually then would sort of match the results of the ODE model to the assumptions a lot better. So absolutely, I think that's an important point.
Yeah.
So Wenlong has been going and finding some of these papers which were not even published.
Yeah, no, I've talked to him about it already. I remember. Yeah, so
I talked to you about this.
Yeah, absolutely.
Yeah. Cool. That's good. That's great. Yeah.
But I really enjoyed the talk, Vikash. It was
Excellent. Thank you again for having me so much. I really appreciate it, and I look forward to the next one sometime, and to update you on what we've been working on. So thank you so much. I appreciate it.
Anytime when you have something to talk about, just let us know. You're on.
Absolutely will do. Thank you.
Yeah. Okay. Thank you. Have a nice weekend.
Take care.
Yeah. Okay.
Thank you.
You guys too.
Yeah. If any of the students that are here want to ask any other more career-related questions, or maybe everybody's leaving. Maybe they just want to work on their PhD. I don't know.
Then they got so inspired now to work on the PhD.
Yeah.
Okay. All right. So yeah. Wenlong, are you feeling all okay?
Oh yeah. Maybe